Hi everybody, this is going to be a flipped mini chapter that we're going to do and just a little explanation about what you should be doing while you are watching a flipped video. Number one, you should have all of your notes out, just like if you were in class. So you should have your packet, you should have whatever paper you usually write on in class. You should have your calculator, and you should have your AP formula packet. You are going to participate in this the way that you would participate in class, meaning that you are going to take notes, you're going to pause and re-watch if you misunderstand something or you need help, and you are going to follow along doing the calculations as I do. This is not, something for you just to watch. So now that we know what we should be doing while we are watching and while we are participating in this lesson, let's get started. So when we're talking about colorimetry and spectrophotometry, before we do that, we really should talk about the nature of light. So light is something that we have on the electromagnetic spectrum, and what we call visible light is what is visible to us, but it's actually a very narrow range. So the visible light spectrum, or the visible part of the electromagnetic spectrum, is only from about 400 to 700 nanometers or so. And nanometers are the way that we measure wavelength. So if we notice, ultraviolet is on the 400 side. So 400 is the violet end of the spectrum. 700 is, or 750 is near infrared. So that 700 is the red side of the spectrum. We also know that violet light is the higher energy. So when we're looking at this, the energy is getting higher as we go towards gamma. And as we go from red down to near infrared, infrared microwaves, and radio waves, this side is the lower energy side of the electromagnetic spectrum. Now, when we are talking about these different amounts of energy for the electromagnetic spectrum, we can also talk about the amounts of energy and what those types of electromagnetic radiation can do in terms of the atoms and molecules. So if we look at the gamma rays are emitted when there is a, when there is a nuclear reaction. X-rays can remove an inner electron, meaning a core electron. Ultraviolet can remove a valence electron. Visible light can also remove an outer electron, but it can also cause electron transitions. This will have to do with the bright line spectrum, which we get when electrons, when they go from the excited state to the ground state. Infrared and near infrared will cause vibrations of either the outer electrons or the molecules. Microwaves have less energy, and that less energy can't cause the electrons and the molecules to move back and forth in vibrations. They can only cause the molecules to rotate. This is actually how your microwave oven works. It actually causes water to rotate, and that rotation warms up the food. And then microwave and radio waves can only cause spin flips of the electrons and the nucleus. These are not things that we need to be concerned with. So basically, as we have lower energy radiation, it can cause less movement. Higher energy radiation can cause more movement of molecules, more movement of electrons, and the highest energy can change the nucleus of the atom, remove inner electrons, and as we have more energy in the radiation, it is able to do things that would require more energy. Now, this goes right along with how we get these different colored fireworks. And we know that as electrons transition from ground state to excited state, they absorb energy. So electrons moving up to the excited state absorbs energy. And when these electrons move back down to the ground state, energy is released as light. And since these electrons in different chemicals are moving different distances, different transitions, and different differences between the electron levels means different colors of light are given off because different amounts of energy are given off. When we want to talk about waves and we want to talk about their properties, we have something called wavelength, which is lambda. Okay. I draw a lambda by making this curve and then making that second line. So this curve and then the second line, it's probably not exactly the right way to draw a lambda, but it's what works for me. And, that's your lambda. It's kind of like a backwards H, and that means wavelength. Frequency is new. If you think about drawing those seagulls in your projects when you were younger, those are very close to news. If you want to just make a squiggly V, that works also. We represent the speed of light as c. This constant and these values are on your formula sheet, so you may want to look at your formula sheet at this point, and on your formula sheet you have all of this written out. We have two formulas: energy of a single photon, which is how this energy and this light is given off. Energy is equal to Planck's constant times nu, and c, which is the speed of light, equals nu times lambda, or lambda times nu. So we can use these formulas in order to find out the amount of energy associated with the color of light that was given off. And as we can see, this is our wavelength here, peak to peak or trough to trough. And in this case, the energy associated or the energy represented by wave B is actually higher energy because it has a shorter wavelength. It says the brilliant red color seen in fireworks. Colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers when strontium salts are heated. This can be easily demonstrated in the lab by dissolving one of these salts in methanol that contains a little water and igniting the mixture in an evaporating dish. And then it asks us to calculate the frequency of red light of wavelength 6.5 times 10 to the 2 nanometers. So I am going to write the 6.5 times 10 to the 2 nanometers, which remember was 650 nanometers. And we want to know the frequency. So this right here is wavelength. Wavelength, remember, is represented by lambda. We want to find the frequency. Frequency is nu. Wavelength needs to be measured in meters, and nu needs to be measured in hertz, also known as cycles per second, or just simply seconds to the -1. So let's just go through that again. Wavelength needs to be measured in meters, and it is abbreviated by lambda. Frequency is measured in seconds to the -1, cycles per second, or hertz, and it is represented by nu. We are trying to find the frequency from the wavelength, so we are going to use the formula from our formula sheet that says C equals lambda nu. Now, I have my wavelength in nanometers. Thankfully, I know that nanometers equals 10 to the -9 meters, right? We memorized these powers of 10 if you have me. So I am going to change my n, right? I'm going to say that it is 6.5 times 10 to the 2 times 10 to the -9 to get my value into meters, right? I take the n out and I multiply by 10 to the -9. So now 10 to the 2 times 10 to the -9 becomes 6.50 times 10 to the -7 meters. Most of our visible light is going to end in 10 to the -7 for our meters for the wavelength. So now that I have my wavelength in meters, I'm going to look up the speed of light. On the formula sheet, and I'm going to plug in my wavelength here, and this is going to be my x. So why don't you put all of that in, looking at your formula sheet, looking at everything else, and see if you can calculate the frequency. So hopefully you have found the speed of light on your formula sheet, and it says 2.998 times 10 to the 8th meters times seconds to the -1 equals 6.50 times 10 to the -7 meters times x. When I divide both sides by my wavelength, right, my meters cancel out, and my unit that I'm left with is seconds to the -1, which is great because that's what I'm supposed to get for frequency. So now I'm going to do this on my calculator, remembering that when I put in 2.998 times 10 to the times 10 to the 8th, I do 2.998 second comma 8. If you have your graphing calculator, if it's a scientific calculator, we are going to use something different. And if you have a scientific calculator, you're going to look for the EE also, and you're going to do, it's going to be second and then the button right above the 7. And that means that you do not have to use you do not have to use parentheses and carets. So now I divide by my 6.5 second comma -7. If I have my graphing calculator, second, I don't know what button it is. Oh, I'm looking at it. Second x to the -1 if you're using a scientific calculator. And when I press enter, I get 4.612307, blah, 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 seconds to the -1. Take a look at your numbers that we put in. See if you can decide how many significant figures this needs. And it should be 3 significant figures because this value had 3 significant figures. And so we are going to call it 4.61 times 10 to the 14th seconds to the -1. Now, does this make sense? 3 divided by 7 gives us that number. 8 minus a -7 would be 15, but this number when we divide is less than 1, which is why we get 10 to the 14. So it looks like a scary, strange number, but it's because of the very, very small number that we were dividing by. So this right here would be our frequency in this question. Now, if we also somehow wanted to find out the energy associated with this, so we're going to pretend that it says calculate the frequency and energy per photon for this light, we would now be able to take this frequency, right, and plug it in to E equals h nu, because this E means the energy per photon of that color of light. H, remember, is Planck's constant, and that is also on your formula sheet under atomic structure. So I am going to keep my 4.61 times 10 to the 14th, the unrounded version. I'm going to keep that in my calculator, and I'm just going to copy this and move it onto a new page so that we can start there. Okay, so this is my frequency, but now on my calculator, it actually says 4.612307,692 times 10 to the 14th seconds to the -1, because remember, we use unrounded values in subsequent calculations. So now that we found the frequency of this red light, if we want to find out the energy associated with a photon of this red light, we're going to plug it into E equals h nu. That's also on your formula sheet. And so we're solving for E. Planck's constant, look at it on your formula sheet. Under atomic structure, says 6.626 times 10 to the -34 joules times seconds. Now that's going to get multiplied by our frequency, which is that 4.61 number, right, times 10 to the 14th seconds to the -1. We're going to keep the number from our calculator here and just multiply by Planck's constant. Notice now that seconds times seconds to the -1 cancel out, giving us the unit of joules, which is a great unit since we're looking for energy. So now I take that number, that unrounded number from my calculator, and I multiply by 6.626, second comma, negative 34 if you're on a graphing calculator, second x to the minus 1, negative 34 if you are on a scientific calculator. And when I press enter, I find out that the energy for one photon with a wavelength of 650 nanometers is 3.06 times 10 to the negative 19 joules. So the original problem told us, right, that the wavelength was 650 nanometers. So that means that we put in the 650 nanometers, we used we didn't use that. We used C equals lambda nu, which allows us to find any wavelength on the electromagnetic spectrum. Plug it into this formula with the speed of light to get the frequency. Then we also know that E equals h nu, where E is the energy for one photon, h is Planck's constant, and nu is the frequency. So we plug the frequency in that we found to here, and now we just need Planck's constant in order to get the energy for that single photon. Now, after doing this, you should be able to work on chapter 7, numbers 42 and 43. So at this point, if you want to, actually, I think I'll stop the video here, and then we can pick up the next video with the next piece of information here.